February 14th, 1944. 37,000 feet above the frozen German countryside. Technical Sergeant Robert Mitchell watches his instruments with growing disbelief as his Boeing B-17G Flying Fortress Thunder Bay climbs higher than any bomber in his squadron has ever flown. The four Wright Cyclone engines scream at maximum power, their turbo superchargers working overtime in the thin air that should have killed them all 10 minutes ago. Below and behind them, 6 Messerschmitt Bf-109 fighters circle in frustrated confusion. The German pilots push their aircraft to maximum performance, clawing desperately for altitude, but their engines sputter and choke in the rarefied atmosphere. At 35,000 feet, their superchargers fail. At 36,000, their controls become sluggish and unresponsive. At 37,000 feet, they can climb no higher while the lone American bomber continues its impossible ascent toward 38,000 feet. "They can't follow us up here," Mitchell shouts over the intercom to his pilot, Lieutenant James Coleman. "Their fighters just don't have the juice." What the German pilots witnessing this incredible sight don't understand is that they're watching the most extraordinary flying achievement of the Second World War. A slow, heavy bomber, supposedly limited to 25,000 feet with a full bomb load, is not only outflying the Luftwaffe's finest interceptors, but doing so while carrying a secret that could change the outcome of the war itself. The story of how Thunder Bay achieved the impossible began 3 weeks earlier in a classified laboratory buried deep beneath Wright Field in Dayton, Ohio, where America's most brilliant aeronautical engineers had been working on a project so sensitive that fewer than 12 people in the entire Army Air Forces knew of its existence. The Luftwaffe's devastating attacks on Allied bomber formations throughout 1943 had forced American military planners to confront an uncomfortable reality. German fighters, particularly the new Focke-Wulf 190 and improved versions of the Messerschmitt Bf-109, could intercept and destroy B-17 formations at any altitude the bombers could reach. Standard operating altitude for heavy bombers ranged from 22,000 to 28,000 feet, well within the performance envelope of German interceptors. German fighter pilots had developed increasingly effective tactics against American bomber formations. They attacked from high altitude, diving through bomber boxes with devastating cannon fire before climbing back to safety. The mathematical reality was stark. German fighters could reach 35,000 feet while maintaining combat effectiveness. American bombers, limited by weight and oxygen requirements, rarely operated above 28,000 feet. This 10,000-foot advantage gave German pilots decisive tactical superiority. The solution emerged from an unlikely source. A 28-year-old engineer named Dr. Sarah Chen, whose doctoral thesis at the California Institute of Technology had focused on high-altitude engine performance. Chen's research into turbo supercharger efficiency at extreme altitudes had been largely theoretical until the Army Air Forces recruited her for the classified Stratosphere project in January 1944. Chen's breakthrough came from understanding a fundamental limitation in existing turbo supercharger systems. Standard B-17 engines used single-stage superchargers that provided adequate performance up to about 25,000 feet, but became increasingly inefficient at higher altitudes. The engines simply couldn't compress enough air to maintain power output in the thin atmosphere above 30,000 feet. Her solution involved a revolutionary two-stage supercharging system that compressed incoming air twice before feeding it to the engine cylinders. The first stage operated continuously, providing baseline supercharging for normal flight operations. The second stage activated only at extreme altitudes, providing additional compression when atmospheric pressure dropped below critical thresholds. The engineering challenges were enormous. The additional supercharger stage increased engine weight by nearly 400 pounds per engine. The system required complex automatic controls to prevent overpressurization that could destroy the engines. Most critically, the enhanced superchargers generated tremendous heat that threatened to melt engine components unless properly managed. Chen's team solved the heat problem through an innovative cooling system that used high-altitude air intake to pre-cool the supercharger stages. The thin, frigid air at extreme altitudes, previously a limitation, became an asset that enabled higher compression ratios without overheating. The system was elegant in its simplicity. The higher the aircraft flew, the more efficient the cooling became. Testing began in February 1944 using a modified B-17G, designated X-17A, for experimental purposes. Initial flights confirmed Chen's theoretical predictions. The aircraft could maintain full power output at altitudes exceeding 35,000 feet, far beyond the capability of any operational bomber. However, the test flights also revealed unexpected challenges that threatened the entire program. The primary problem was human, rather than mechanical. At 35,000 feet, even with oxygen masks, aircrews suffered from altitude sickness that impaired their ability to operate effectively. The unpressurized bomber cabin subjected crew members to environmental conditions equivalent to climbing Mount Everest while performing complex technical tasks under enemy fire. Chen's team developed specialized high-altitude survival equipment for the bomber crews. Enhanced oxygen systems provided pure oxygen at higher pressures than standard aircraft equipment. Heated flight suits protected crew members from temperatures that could reach 60 degrees below 0 Fahrenheit. Most importantly, they created rapid descent procedures that would allow bombers to drop quickly to safer altitudes if crew members became incapacitated. The first operational test came when Thunder Bay, equipped with Chen's experimental supercharger system, was assigned to the 306th Bomb Group for a maximum security mission. Only Lieutenant Coleman and Technical Sergeant Mitchell knew about the aircraft's special capabilities. The rest of the crew believed they were flying a standard B-17G on a routine reconnaissance mission over occupied France. Mission briefing on February 14th revealed a target that made every airman in the room nervous: a heavily defended aircraft factory near Leipzig, deep in the heart of Germany. Intelligence reports indicated that the facility was surrounded by more than 200 anti-aircraft guns and defended by at least 50 German fighters. Previous bombing attempts had resulted in catastrophic losses, with some formations losing more than 30% of their aircraft. Coleman's orders were specific but cryptic: maintain formation with the rest of the bomb group until crossing into German airspace, then climb to maximum altitude and proceed independently to the target. The official reason given was experimental high-altitude bombing techniques, but Coleman understood that Thunder Bay was testing something far more significant than new bombing procedures. The mission launched at 0630 hours, with 36 B-17s forming up over the English countryside. Thunder Bay flew in the high squadron position, appearing identical to every other fortress in the formation. As they crossed the channel and approached the German border, Coleman began his climb according to orders. At first, the ascent seemed routine. Thunder Bay pulled ahead of the formation as it gained altitude, standard procedure for aircraft climbing to higher bombing altitudes. At 28,000 feet, the normal service ceiling for a loaded B-17, Coleman engaged Chen's experimental supercharger system. The effect was immediate and dramatic. Instead of losing power as they climbed higher, Thunder Bay's engines actually seemed to become more efficient. The aircraft continued climbing at a rate that should have been impossible for a heavy bomber. Mitchell watched his altimeter pass 30,000 feet, then 32,000, then 35,000 with no decrease in engine performance. Below them, the main bomber formation continued toward Leipzig at 26,000 feet, already under attack from German fighters that had climbed from airfields across central Germany. Coleman could see Messerschmitt and Focke-Wulf fighters diving through the bomber boxes, their cannon fire creating bright flashes among the American aircraft. Several B-17s were already trailing smoke and dropping out of formation. "Bandits, 11 o'clock high," called the top turret gunner over the intercom. "6 of them, climbing toward us." Coleman watched the German fighters approach, noting their steep climb angle and the black smoke trailing from their exhausts as their pilots pushed their engines to maximum power. At 35,000 feet, The first Messerschmitt began to waver as its engine struggled in the thin air. At 36,000 feet, two more fighters fell behind, their pilots unable to maintain the climb rate necessary to intercept Thunder Bay. "They're falling back," Mitchell reported with amazement. "Their engines can't take this altitude." The remaining three German fighters continued climbing, their pilots determined to intercept the lone American bomber that had somehow climbed beyond their normal operational ceiling. At 37,000 feet, even these aircraft began to struggle. Their controls became sluggish in the thin air. Their engines lost power as the fuel-air mixture became too lean for efficient combustion. Coleman pushed Thunder Bay even higher, reaching 38,000 feet before leveling off for the bombing run. At this altitude, the aircraft was flying in atmospheric conditions never before experienced by an operational bomber. The temperature outside reached 70 degrees below 0 Fahrenheit. The atmospheric pressure was less than 1/5 that at sea level. Yet Chen's supercharger system continued to perform flawlessly. The engines maintained full power output despite the extreme conditions. The automatic control systems adjusted fuel flow and timing to compensate for the thin air. Most remarkably, the cooling effect of the frigid atmosphere actually improved engine efficiency, allowing higher boost pressures than would have been possible at lower altitudes. The German fighters, meanwhile, had reached their absolute performance limits. Three aircraft struggled to maintain altitude at 36,000 feet, their engines running rough, and their pilots fighting hypoxia despite oxygen masks. The Messerschmitt Bf. 109's maximum service ceiling was listed as 37,000 feet under ideal conditions, but with combat loads and worn engines, most aircraft could barely reach 35,000 feet. Thunder Bay's bombardier, Sergeant William Torres, found that the extreme altitude actually improved bombing accuracy. The thin air reduced atmospheric disturbance that normally affected bomb trajectories. Wind speeds at 38,000 feet were more predictable than at lower altitudes. Most importantly, the aircraft was so high that German anti-aircraft guns couldn't track it effectively. "Bomb bay doors open," Torres announced over the intercom. "Target in sight." "This is the clearest view I've ever had of a target." The bombing run proceeded with surreal calm. At 38,000 feet, Thunder Bay was virtually untouchable by German defenses. Anti-aircraft shells burst harmlessly thousands of feet below. The few German fighters that had managed to climb above 35,000 feet could barely maintain flight, let alone execute attack runs against a fast-moving bomber. Torres released 12 500-pound bombs with precision that exceeded anything achieved in previous high-altitude attacks. The weapons fell for nearly 90 seconds before impacting the aircraft factory with devastating accuracy. Secondary explosions indicated that the bombs had struck critical production facilities, achieving the mission objectives with a single aircraft that previous raids had failed to accomplish with dozens of bombers. The return flight proved even more remarkable than the outbound leg. Coleman began a gradual descent toward England, but maintained altitude well above the reach of German interceptors. Several fighter squadrons scrambled to intercept Thunder Bay as it crossed central Germany, but none could climb high enough to engage the bomber effectively. At 35,000 feet, German radar operators lost contact with the aircraft intermittently as atmospheric conditions interfered with their tracking equipment. Ground-based anti-aircraft guns couldn't engage targets above 30,000 feet with any accuracy. Thunder Bay had effectively entered a zone of invulnerability that German defenses couldn't penetrate. The psychological impact on German fighter pilots was profound. Experienced aces who had dominated the skies over Europe for years found themselves helplessly watching an American bomber fly beyond their reach. Several pilots reported the incident to their commanders, describing an enemy aircraft that seemed to possess impossible performance characteristics. German intelligence officers initially dismissed these reports as pilot error or misidentification. The idea that American bombers could outperform German fighters at high altitude contradicted everything they understood about Allied aircraft capabilities. Only after multiple similar reports from different fighter units did German analysts begin to suspect that the Americans had developed some kind of enhanced bomber variant. the intelligence failure was critical. German defensive planning assumed that American bombers would continue operating at altitudes below 30,000 feet, where German fighters could engage them effectively. The possibility that bombers might climb beyond interceptor range had never been seriously considered by Luftwaffe tactical planners. Thunder Bay landed at its base in England after a mission duration of 8 hours and 47 minutes. The aircraft had flown deeper into German territory than any previous bomber mission, while suffering no damage whatsoever from enemy action. The crew reported no equipment failures and only minor fatigue from the extreme altitude operations. Post-mission analysis revealed the full significance of Chen's achievement. Thunder Bay had operated at altitudes where German fighters couldn't follow, anti-aircraft guns couldn't reach, and radar systems couldn't track reliably. The experimental supercharger system had effectively made the bomber invulnerable to existing German air defense systems. More importantly, the mission demonstrated that strategic bombing could be conducted with acceptable losses if bombers could operate above enemy fighter intercept capability. Previous bombing campaigns had suffered catastrophic casualty rates because bombers had to fly within range of German defensive systems. Thunder Bay's success suggested that high-altitude operations could revolutionize strategic bombing effectiveness. The implications extended beyond immediate tactical advantages. German war production relied on the assumption that critical facilities could be defended by conventional air defense systems. If American bombers could operate beyond the reach of these defenses, virtually every important target in Germany became vulnerable to precision attack. Chen's supercharger system underwent rapid development for mass production. By March 1944, modified B-17s, equipped with the enhanced engines, began appearing in small numbers with selected bomb groups. The aircraft were designated B-17H internally, though they maintained the appearance of standard G-model fortresses to preserve operational security. Training programs prepared bomber crews for high-altitude operations that exceeded normal human endurance limits. Pilots learned to manage engines operating at performance levels never before attempted in combat aircraft. Navigators studied atmospheric conditions at extreme altitudes where standard weather patterns didn't apply. Bombardiers practiced precision bombing from heights that required entirely new targeting techniques. The first formation mission using B-17H aircraft occurred on March 25, 1944, when 12 modified bombers attacked aircraft production facilities near Munich. Flying at 39,000 feet, the formation completed its mission without encountering a single German fighter. Anti-aircraft fire burst ineffectively far below the bombers, creating spectacular but harmless displays of exploding shells. German defensive responses evolved slowly as the extent of American high-altitude capabilities became apparent. Some fighter units received modified aircraft with enhanced superchargers that could reach 38,000 feet, but these modifications compromised low-altitude performance and required extensive maintenance. The German aircraft industry lacked the resources to develop completely new high-altitude interceptors while simultaneously maintaining production of existing fighter types. By April 1944, American high-altitude bombing operations had fundamentally altered the strategic balance over Europe. German fighters, previously the primary threat to Allied bomber formations, could no longer reliably intercept targets flying above 35,000 feet. The psychological effect on German pilots was devastating, as experienced aces found their aircraft outclassed by enemy bombers they couldn't even reach. The technical achievement represented by Chen's supercharger system influenced post-war aviation development for decades. The principles of multi-stage supercharging became standard in military aircraft designed for high-altitude operations. Commercial aviation adopted similar technologies for passenger aircraft operating at altitudes where fuel efficiency improved dramatically. Modern jet engines incorporate supercharging concepts that trace directly to Chen's wartime innovations. The understanding that extreme altitude could become an operational advantage rather than a limitation influenced strategic bomber design throughout the Cold War period. Aircraft like the Lockheed U-2 and Boeing B-52 utilized similar principles to operate beyond the reach of enemy interceptors. The human factors research conducted for the B-17H program contributed to pressure suit development that eventually enabled space exploration. The life support systems designed for bomber crews operating at 40,000 feet provided the foundation for equipment that allowed astronauts to survive in space. The connection between wartime high-altitude bombing and the space program demonstrates how military innovation drives technological progress across multiple fields. Dr. Sarah Chen received the Distinguished Service Medal for her contributions to strategic bombing effectiveness, though the classified nature of her work meant that public recognition came only decades after the war ended. Her theoretical research into supercharger efficiency had practical applications that extended far beyond the original academic context, illustrating how fundamental science drives practical innovation. Thunder Bay itself completed 14 more high-altitude missions before war's end, never suffering significant damage from enemy action. The aircraft became a legend among bomber crews, though operational security prevented widespread knowledge of its unique capabilities. Post-war analysis revealed that B-17H aircraft had achieved bombing accuracy rates nearly double those of conventional bombers, while suffering loss rates approaching zero. The German fighter pilots who first encountered Thunder Bay at 37,000 feet never learned the technical explanation for what they witnessed. To them, it remained an inexplicable phenomenon, an American bomber that somehow flew faster and higher than their fighters could follow. Several pilots included the incident in their memoirs, describing an enemy aircraft that seemed to possess supernatural performance characteristics. Lieutenant Coleman and Technical Sergeant Mitchell flew together for the remainder of the war, completing 25 missions without losing a single crew member to enemy action. Their partnership demonstrated how revolutionary technology requires skilled operators who understand both the capabilities and limitations of advanced systems. The success of high-altitude bombing operations depended as much on crew expertise as on engineering innovation. The strategic impact of high-altitude bombing extended beyond immediate military objectives to influence German war production planning. Facilities previously considered safe from Allied attack required expensive defensive measures that diverted resources from offensive operations. The psychological effect on German civilian morale was equally significant, as populations realized that no target was beyond Allied reach. By June 1944, German intelligence had identified the general nature of American high-altitude bomber modifications, but lacked the industrial capacity to develop effective countermeasures. The Reich's aircraft industry was already operating at maximum capacity to maintain production of existing fighter types. Developing new high-altitude interceptors would have required abandoning production of aircraft needed for immediate defensive operations. The tactical revolution represented by high-altitude bombing influenced Allied invasion planning for Europe. Knowing that strategic targets could be attacked with minimal losses allowed military planners to focus fighter escorts on ground support operations rather than bomber protection. This concentration of fighter strength proved crucial during the Normandy landings, where Allied air superiority enabled successful amphibious operations. Thunder Bay's final mission occurred on April 28, 1945, just 10 days before Germany's surrender. Flying at 40,000 feet over Berlin, the bomber participated in a demonstration flight intended to show German leaders that Allied aircraft could operate with complete impunity over the Reich's capital. The mission required no weapons. The mere presence of American bombers flying beyond the reach of German defenses provided sufficient psychological impact. Post-war interviews with German fighter pilots revealed the profound impact of high-altitude bomber operations on Luftwaffe morale. Experienced pilots described the frustration of watching enemy aircraft operate beyond their reach, undermining confidence in German defensive capabilities. Several pilots specifically mentioned incidents where American bombers climbed beyond interceptor range, disappearing into the stratosphere like ghosts in the sky. The technological legacy of Chen's supercharger innovation influenced military aviation development throughout the Cold War period. Soviet engineers studied captured B-17H aircraft to understand American high-altitude capabilities, leading to their own development of high-altitude interceptors and strategic bombers. The competition to operate at extreme altitudes became a defining characteristic of military aviation during the 1950s and 60s. Modern aviation owes significant debt to the innovations developed for high-altitude bombing operations. Commercial airliners routinely operate at altitudes that were considered experimental during World War II. The life support systems, pressurization technologies, and engine management techniques pioneered for military applications became standard features of civilian aircraft. Dr. Chen continued her research into high-altitude engine performance after the war, contributing to the development of jet engines and rocket propulsion systems. Her understanding of atmospheric effects on engine operation proved crucial for aircraft designed to operate at the edge of space. The transition from propeller-driven aircraft to jets, and eventually to rockets, followed logical progression from her wartime innovations. The story of Thunder Bay illustrates how individual innovation can influence the outcome of global conflicts. A single engineer's theoretical research, applied under wartime pressure, created tactical advantages that affected strategic planning at the highest levels. The bomber that outflew German fighters achieved more than temporary tactical success. It demonstrated technological superiority that influenced enemy decision-making and resource allocation. On February 14, 1944, at 37,000 feet above frozen Germany, Technical Sergeant Mitchell watched German fighters fall behind and realized he was witnessing history in the making. The slow bomber that wasn't supposed to outperform enemy interceptors had just redefined the rules of aerial warfare. Thunder Bay proved that innovation, properly applied under extreme circumstances, could achieve results that seemed impossible according to conventional understanding. The Luftwaffe pilots circling helplessly below would remember that day as the moment they realized the war in the air had changed forever. American bombers could now fly beyond their reach, operate with impunity over defended targets, and strike critical facilities without risking catastrophic losses. The age of high-altitude strategic bombing had begun, and with it, a new chapter in the technological competition that would define modern warfare for generations to come.